share my screen?
Yes, please.
Let's see, how do I do that? Is it in the share tray? Yeah, I guess I'll just do that. Can you see my screen?
Yeah.
Cool.
Yes.
Okay. Let me get started. Okay, cool. So today I'll be talking about continuously indexed normalizing flows, which is a model for improving upon baseline normalizing flows by relaxing their bijectivity constraint. So I presented this yesterday at a different research group as well. It was a slightly longer version, so I might go through some of the slides kind of quickly, but so please feel free to interrupt me if you have questions. So I'll quickly give a roadmap of what we're going to do. So normalizing flows are bijections, and they give you an explicit density model. This is convenient computationally when you're doing density estimation, but since they're bijective, it provably limits their expressiveness, or at least the expressiveness of the resulting density models. So what we are proposing to do instead is augmenting standard flows with auxiliary variables, which now gives you an implicit density model, but one that's more expressive and is no longer strictly bijective. And we call these continuously indexed normalizing flows. Cool. So first I'll give some context. So we're mostly concerned about the setting of density estimation here, although we will touch on variational inference as well. So the typical density estimation setting is you have a data set where each point is coming from some data set or some data space. And we assume that each point is sampled independently from some target distribution over this space. So density estimation is the problem of using some model, we'll call PX, to estimate this target P star X. So there's a bunch of applications of density estimation. I probably don't have to go through them all. If you have a model of your data set that's really good, then you can imagine that helps you in a lot of ways, even for predictive modeling or anomaly detection and so on. And here I've just put a picture of a simple density estimation model in one dimension. This is a histogram, which can be considered a density estimator as well. And then they fit a kernel density estimator on top that smooths out the histogram. So, like I said, in low dimensions, like that example we saw, we have density estimators such as scaled histograms or kernel density estimators, which are also known as parson windows. But these methods don't really scale up to high dimensions because of the cursed dimensionality. So what will be focused on more in this talk are high dimensional density estimators and specifically normalizing flows, which have shown some very good results in generating images and also density modeling of data sets. Some related methods are variational autoencoders, which prescribe a low dimensional latent space and probabilistically map to a higher dimensional space. And also energy-based models, which propose a Boltzmann style distribution that has to be learned. So both of these two methods, not highlighted, have either inexact likelihoods or likelihoods that you can't compute. Likelihoods that you can't compute exactly anyway, whereas normalizing flows have exact likelihoods. So density models are also useful in variational inference. Probably don't have to go too into detail, but the Bayesian inference setting here, I'll write the joint model that you have for Bayesian inference as PXY, where the data is now Y and the latent is X. So the reason I'm using this notation, which is like a more traditional STATSy notation, as opposed to the machine learning PXZ, is because if I keep X the same here, then I can use the same CIF formulation for density estimation and VI. So anyway, when you're doing Bayesian inference, you're given this joint model, and you want to now use the posterior px given y to usually compute some expectations. But this posterior is typically intractable and difficult to sample from. So now enter variational inference, where we introduce a parameterized density model Q as an approximation to the posterior. And you've now, to perform inference now, we instead do optimization of the parameters of Q. So that's one other way that density models can be used. And in fact, normalizing flows are used in this setting as well. Cool. Are there any questions on that? Okay, I'll proceed. So now we have, let's think about standard normalizing flows. I'll describe them and then talk about some pathologies. So what is the model that normalizing flows propose? Well, the density model proposed by normalizing flows is sample first from some simple distribution, let's say a standard normal over the latent space, and then push this forward by a bijection to model your data. And this bijection is often called a flow. That's the normalizing flow part. This flow is a parameterized diffeomorphism or a differentiable bijection. And the goal is to learn the parameters of f to get a good model of your density x. How do we learn these parameters? Well, we can perform maximum likelihood estimation because we have the change of variable formula. So we know that the density, since f is a bijection, can be represented in the following form: a prior term times the volume change. And here just some notation. I've used df inverse to denote the Jacobian of f inverse. So that's nice and easy. In case you're not totally familiar. Oh, sorry.
Oh, sorry for the noise. Is this notation standard in any way? It looks quite pretty.
Oh, the D, you mean? The DF? Yeah. I don't know. So sometimes people use a J and then put the F inverse as a subscript. I like using the D because it separates the function from the evaluation.
Yeah.
People use also partial F inverse over partial X, or they might say partial Z over partial X. I find that to be very confusing. It's not really clear to me at all what the difference between the function and the evaluation.
Yeah, yeah. I will consider using this notation. It looks quite, as you say, that's quite intuitive.
Cool. Yeah. Great. Yeah, it's good to use. I feel like the notation can sometimes be cleaned up in machine learning, so it's nice when something works out.
Tell me about it. 1/3 of the effort lately I have is just defining the notation. It's just, especially with tensors, so we don't have the right one.
Yeah, it's a pain. I think there's some improvements happening though. Anyway, let's proceed with some examples of normalizing flow layers. So just to give some context of what these flows could look like. So one example is the real MVP layer. So you partition your latent space variable into two groups, and then you pass the first group through unchanged. And then the second group you modify using a shift and scale operation, where the shift and scale are dependent on the first group. So what's important about this is that this is invertible. It's not hard to show that at all. And the Jacobian is also very easy to compute. So the log determinant of the Jacobian would be simply the product of the components of S. So that's quite straightforward. Another example is called Fjord, where the flow F is now the flow of an ODE, which is induced by a parameterized vector field. So the goal is to learn the parameters of the vector field that drive the flow. And this is invertible because of the uniqueness of ODE solutions from starting from different initial conditions. So that's nice as well. And then a final example is the residual flow or res flow, where F is defined as a residual network. So this is a normal form of a resonant, except with the catch that G is constrained to have Lipschitz constant less than 1. And how this is enforced is through some kind of spectral normalization on the weights. But what's important to note is that if G has a Lipschitz constant less than 1, then it's not hard to see that F is always invertible. Because the overall Lipschitz constant has to be positive. I think there might be some additional conditions, I'm not totally sure. But anyway, it works out in practice.
Does the enforcement of the Lipschitz constant actually work? Because I remember this used a lot in Wasserstein-Gahn, and I always felt I wasn't sure I was actually enforcing any Lipschitz constant or just doing some random stuff on the network.
So I think I do think actually the Lipschitz constant works fairly well, the Lipschitz enforcement. I think the if I recall correctly, the problem with Wasserstein-Gahn is that it's not actually estimating any sense of a Wasserstein distance. Or at least maybe not the problem, but that's like one of the concerns I've heard. I've never really heard that the Lipschitzness was not being enforced, but maybe your experience has been a bit different. Well, I've never actually worked with them, to be honest. So
if you could constrain the Lipschitz constant exactly, then you will at least in theory converge to the Wasserstein distance. The problem is that the problem in Wasserstein-Gahn, sorry, maybe I'm going for a tangent, but the problem there is that the constraints that your architecture has is much more than the constraint of Lipschitzianity. So basically, it is the whole fact that using convolutional network is constraining the functional space much more than the other constraint. Therefore, you're optimizing some divergence, but not necessarily the Wasserstein one. But,
right. Yeah. So this here, we're not really concerned about what divergence we're optimizing, really. We just care that G has Lipschitz constant less than 1. I think in practice, they try to target a Lipschitz constant of like 0.9. So that it's, as long as it's less than 1, it's fine for them. I think it's a slightly simpler setting. Cool. Okay. So normalizing flows, they have some nice properties. So first of all, assuming you have a tractable Jacobian determinant, then the density of your normalizing flow model is quite easy to evaluate for any x. We can just use the change of variable formula. So this is very useful in training the model because we can use maximum likelihood and test time evaluation, because given a new point, we can easily assess the density of that point. And you can also stack these models quite easily. They're kind of interchangeable. If you have several bijections in a row, it's still a bijection. And you can also add up all of the contributions of the log Jacobians. But one issue that bijectivity imposes is that the support of your model has the same topological properties as the support of your prior. So this is a bit problematic because your prior is typically a simple distribution, like a standard normal. And so if you want to model any sort of complicated densities, this is suggesting that maybe normalizing flows are not the tool that you should be using, because they might be a bit misspecified in that regard. They can still get close, but this is kind of saying, well, maybe they're a bit underpowered from the start in that regard. And let's see some example. Well, first, actually, the theoretical result. So the this is a more concrete version of what I was just saying. So we've shown that if the prior has non-homeomorphic support to the target, then a sequence of normalizing flow models will converge in distribution to the target only if the Lipschitz constant of the flow or the Lipschitz constant of the flow inverse approaches infinity. So what does this mean in practice? or in plain English at least. So to exactly match a complicated target distribution, a normalizing flow must approach numerical non-invertibility. And I could even remove numerical here. It could just be even theoretical non-invertibility. So what are the implications? So actually a somewhat recent paper has observed non-invertibility of flows in practice. I can't remember the title exactly of this paper, but it was, I believe, a NeurIPS submission, 2020. They pinpointed a lot of problems with non-invertibility in normalizing flows. They don't really have a lot of solutions in that regard, though. So flows have to become numerically non-invertible to exactly match their target, but some flows are quite constrained so that they could never become numerically non-invertible, like the res flow with if you keep the number of layers quite low. So what you'll see, if your flow is constrained so that it can't become numerically non-invertible, you'll observe some underfitting of your models. And in any case, you might observe some instability as well. Anybody who's worked with normalizing flows has probably at some point had some problems with stability in training. Cool. Are there questions on this? No? Okay. I will proceed to a practical example. So here's the res flow again. We take a Gaussian prior and use 10 layers of the res flow, as noted before. So here we're trying to learn two densities, so we only have access to the data, right? On the left, you have two uniform rectangles that are well separated. And then on the right, you have an annulus distribution, again, uniform along the annulus. So we can see that the density models output by these methods have a couple major artifacts. The first one is that there's a lot of density connecting the two regions on this left-hand side. So this should be zero density right in the middle. And why does this happen? Well, if we think about the fact that our prior is a Gaussian in 2 dimensions, so it's basically a disk, let's say in the middle here. Every point in this disk has to go either to the left or to the right. So then at some point in the middle, there should be, to perfectly model this density, you need to instantly switch from going to the left, then to the right. But that violates Lipschitzness, it violates continuity. So in practice, what you see is that there's this space in the middle where some points haven't made it all the way, basically. Does that make sense?
Yep.
Cool. Okay, and then the other problem that we see here, so we don't see this mass problem as much over here. Maybe in the center, it's numerically basically zero. But in both images, what we see is a lot of patchiness in the density. If this was a good density model, this would all be the same color, or at least close to the same color. And we see even more patchiness in this ring example. So we want to hopefully clean this up. And how would we do that? Well, we could use continuously indexed normalizing flows. So let's just present the model first of all. The continuously indexed model is the same as a normalizing flow, except for 2 differences. So the first one is that we have this continuous indexing happening at each layer. This U is new over the previous generative process. This PU given Z is some trainable distribution. And the second thing that's different is this this capital F. So X is the result of applying F to Z and U. And what is F? Well, F is itself a normalizing flow for every value of U. So how do we come up with such a capital F? Well, one simple thing that we use in the paper leverages existing normalizing flows, little f, let's say. We can now define our capital F as little f applied to a shifted and scaled version of our input z. So now these neural networks S and T are mapping from U space to Z space, and this circled dot is a element-wise multiplication. So we can see that if if S and T were outputting all zeros, then this would just be the model produced by a baseline normalizing flow. It would just be F applied to Z. So we can see that in this way, the continuously indexed construction strictly generalizes the baseline normalizing flows. Cool. Are there questions on the model? Okay. So now, like in baseline normalizing flows, we can stack the CIF construction repeatedly. So what we're going to do is take these last two steps and repeat them over and over again. So again, remember, we're trying to model a value of x. So we're building a generative model up for this x. So we start by sampling from a simple distribution. Then we sample our first u value, condition on the previous z value. And then given z0 and u1, then we know z1 exactly, because this f, capital F, is deterministic given the previous two values. And then we continue this process all the way down until we reach our x value. You can see it graphically here. The circle nodes represent random values, and the diamond nodes represent deterministic values given their parents. And another thing we can see is that if we remove all these u values, then we're just left with a standard normalizing flow model. Cool.
Sorry, if you go to the previous slide, can you please define once more what U is exactly?
U is a random variable defined over some space calligraphic U. This is typically a lower dimensional space than the Z and X spaces. And this PU given Z is typically going to be something like a VAE style encoder. So in other words, take your Z, apply a neural network to it, and then output the mean and standard deviation of a Gaussian distribution. Does that make sense?
Yes, thank you.
Cool, no problem. Are there other questions on the single layer or multi-layer model?
So maybe because this is, as you know, we're also working on similar models in the past. Of course, not in this level of depth, and because mostly our interest was solving other problems, and this was part of the solution. Do you think there is a big advantage in using multi-layer levels of this indexing instead of having all of them in the bottom layer?
So practically, we see a huge difference, but maybe. Actually, I guess the big difference is if you use multi-layers of indexing, the inference of the U values gets easier because you have additional structure and you're able to invert the model correctly up to some distribution that you have to define from like X to UL, which I'll get into a little bit later. But I think the main advantage of stacking in this way, as opposed to having everything at the start, is that you get the advantage in your inference. I think hopefully it becomes a bit more clear later. Because if you had all these U's stacked up at the start, you wouldn't have enough structure to infer the U's from the X values, I think. That would be my intuition, at least. And practically, we saw a huge improvement having U's everywhere, as opposed to having U's just at the start or just at the end, or just one block of this triangle structure.
Also, you're using a very specific form for the U. While the solution we are using is to treat the U at the same level as the original variables, and to pair that with very expressive architectures. For example, in our cascading flow paper, we have fully connected architectures. And third idea is that basically you let the universal approximator property of the network kick in at the limit of large number of auxiliaries. Do you see a big advantage in having this specific structuring of the auxiliary?
So do you mean in terms of like how I've defined PU given Z, or do you mean in terms of this, this triangle?
F.
Oh, in terms of F. Oh, yeah. So I think one of the ways that this could be improved really is different structures for capital F. I think that that this is kind of just, this is the second thing that we came up with. The first thing was like putting U as an additional thing onto Z, like concatenating U onto Z, which had some mixed results. This shift and scale was a bit better at modeling data, but I think there's a definitely room for really improving on the structure of capital F.
Yeah, because we're currently concatenating, and well, that works well, but it's a very different setting because we are working on inference, variational inference, and in my experience, performance of flow in variational inference doesn't extrapolate as much in performance of flow in density estimation. Actually, something I would like to investigate. It's just that the task is very different, the training loss is very different.
Yeah, example, I have a bit actually on variational inference at the end as well.
Thank you very much.
Yeah, no problem. Cool. Okay, so let me continue then. Let's see. So of course, now this structure is quite nice, but we don't get it for free. Our marginal distribution Px now is intractable because it's an integral over this tractable joint distribution. But luckily, the joint has a closed form, and it's a nice recursive form that helps with computation. So now, to train these models, we will actually use variational inference, but this is not the variational inference that I was talking about just a second ago. It's a little bit different, but let's just focus on this for now. So since our joint is intractable and we want to actually maximize marginal likelihood, we have to integrate out the U variables. So if we're given an inference model QU given X, we can use the elbow now to train the model, and the elbow is given here. And the elbow is a lower bound on the marginal likelihood, as we know. And an important point of the elbow is that the better your inference model is, then the less bias you'll have in this lower bound, or the less slackness you'll have. So you want to have a well-structured inference model to be able to train this model well. And another point is, although this marginal is intractable, at test time we can still estimate the marginal to arbitrary precision using basically self-normalized importance sampling, because that estimator is consistent with Q as the proposal. Now, in practice, we use 100 or 1,000 samples for some of the really high dimensional data, and it's fine. So now let's talk about the inference model. So I was talking about it a bit earlier, that the reason why we use this structure is so that we can invert it nicely. And that's kind of the whole point of that triangle structure. We can, since we, let's actually go back to that graph. So now we want to infer all of the U values given an X, right? So naively, we could have just used a, let's say any sort of inference model like a VAE style encoder to take in X and then output all the U's. But we have more structure in the model. For example, if we know X and we know UL, then we immediately know ZL minus 1 because of the bijective properties. So what we're going to do instead is go layer by layer and take, let's say we have our X first, we'll infer UL, then we get ZL minus 1 exactly. Then we'll use ZL minus 1 to infer UL minus 1. Then we'll get ZL minus 2 exactly. and so on and so forth, all the way up the chain until we get to U1. And that's exactly what we show here. The relationship, so we can see, for example, once we have X or ZL and UL, then we exactly have ZL minus 1 if we invert this F on its first argument. And we can write it more compactly in this form. What's interesting about this construction, beyond the fact that we've inverted the model correctly, is that we now have a kind of a weight sharing scheme, because both directions, both the forward model and the inference model, use these same FLs, although in the opposite direction. So despite, one thing I should clear up, despite the fact that we invert the model correctly, at least the structure, we still have to introduce these Q distributions. So this will cause our model to be not the exact posterior. The exact posterior would have a P here, but PUL given ZL, for example, is intractable. So we have to replace it with a Q. Does that make sense? Seems like it. Okay, cool. So some benefits of this construction over standard flows. The first intuitive benefit is that PU given Z allows a CIF to quote unquote clean up mass that would be misplaced by a single bijection. So what that means is you're able to use the, let me go back to the model. Sorry for jumping around a bit. This PU given Z can essentially allow you to choose which bijection you want. Let's say in the case of discrete variables, let's say you had two bijections, one mapping to either side of the rectangle. This PU given Z could allow you to choose which bijection to take and basically switch instantly. Maybe not, I mean, the distribution is still continuous, but that's kind of the intuitive benefit. So so to kind of clear this up a bit more, under mild conditions on the target, Px star and F, our bijection, there is some choice of PU given Z such that the model has the same support as our target distribution. So that's already better than the normalizing flow context, where we can't assume that our supports will be the same. We can't even expect them to be the same because of the numerical non-invertibility. And then there's this other proposition, I'll skip it. It's not important. Another thing that's interesting here is that CIFs can be understood as a bit of a hybrid between normalizing flow and VAE density models. So as I said before, a CIF, or normalizing flow, is like a CIF without the U. And then there's a way to think of a VAE in this way as well. If U is your lower dimensional latent space and Z is a standard normal, and your X is let's say a normal VAE with submean and covariance. And then the CIF model adds an edge between the higher dimensional space and the lower dimensional space in this generative process. We can see experimentally that we truly do clean up the misplaced mass and smooth out the mass that's in the modes as well already. So on the top, we have the ones we saw before, and then now we have a CIF version of the same res flow. It only adds a marginal number of parameters on top, and we can see that all the mass in the center is gone, and these modes are more faithfully represented. This more uniform within the modes themselves. And we see the same thing over here. There's less mass now in the center of this annulus, and the mass is more uniformly distributed around the annulus, whereas this one is more patchy. And I have more 2D experiments here with a masked autoregressive flow, which is like a real MVP. We see that the math examples across the top are not very good. Going from this one in the middle to this one over here involves using a higher capacity model. And somehow the higher capacity model has done even worse, which kind of speaks to some instability whereas CIF has cleaned up the result right here. We can see on this 8 Gaussians, this density is way better represented. On the spiral one, this bottom one is better than this top one, but it's still not very good. But then when we increase the capacity of the model, we can model the spiral, not perfectly, but pretty close, and which is way better than what's up here. Then we have some image data set results for the classic density estimation problems. I don't want to focus on this too much, but the point to note is that the CIF, so the CIF is the same as the res flow construction in the CIF res flow is the same as the small res flow. So we add some CIF stuff on top of a small res flow and get large improvements. And then when we increase the capacity of the res flow, this one does better than the small variant, but still not as good as the CIF version. So these two at the bottom are meant to have about the same computational complexity. And we have a litany of other experiments in the paper that you can check out.
So I always felt intuitively that the biggest benefit of auxiliaries is in lower dimension, because the topology of lower dimensionality is much more constrained. And while if you have very high dimensional spaces, then yeah, continuity, it's a more relative concept, since you can sneak in, you can connect things in a much less visible way. And also the way I also see that in the term again of universal approximation, in the sense that the dimension eventually give you the width of the network. And if there is already a very high width, it means that the network has much more representational capability than if the width is very low, like in low dimensional cases. So do you think that this kind of auxiliary models are still useful in very high dimensions, like very big images?
Yeah, so I guess I would have a counterpoint. So I guess your intuition on topology is true for low dimensions, but I think in high dimensions, the problem can get even worse for topology, because you have, for example, if you think about the MNIST data set, there is no way that this is topologically equivalent to all of RD, or whatever its dimension is. Like, I would be shocked, so to speak, if that was the case. I think there has to be some really interesting topological structure in that model, or sorry, in that data set. Although it's a bit more, this is a bit more conjectural, right? I think there has to be a lot of structure that's being missed by mapping from a normalizing flow in the ambient space onto itself. Does that make sense?
Yeah, no, indeed. And I think there are two separate problems, which one is the bimodality, which is mostly a problem in low dimension, as you argued before. But the other is what you mentioned now, the fact that image manifolds can live in quite lower dimensionality as the pixel space. So it will make a lot of sense indeed. That, for example, when people train by on MNIST, they often use inner dimensionality that is like 2 or 3, that is extremely low compared with the 28 by 28 number.
Yeah.
And that's all. I always felt that that's a reason why VAE work. Let's be honest, VAEs are easier to train than normalizing flows at the moment.
Yeah, true.
And yeah, that's a very good point. I do feel that adding auxiliaries, but the fact that even if you add auxiliaries, you cannot reduce the dimensionality, right? And that's the biggest problem of VAEs, of normalizing flows, that you can increase. Okay, for low dimensional, you can increase the dimensionality, and that's nice. And in low dimensional works very well. I also have a lot of experience in inference there. But I wish we had a method for actually decreasing the dimensionality in a way that is compatible with the philosophy of the normalizing flow approach.
So I'm actually working on something kind of like this, but I think to kind of still talk about the CIF first, I think I think the auxiliaries maybe can help at least reassign mass. So by the normalizing flow from ambient space to ambient space, it's still going to end up having this high dimensionality output. But I think the auxiliaries they have the stochasticity. So in principle, they could reassign mass to, I think, lower dimensional spaces. In principle.
By creating.
I'm not totally sure. I'm not. This is more conjectural. I'm not totally sure, actually. As I'm saying it, I'm not convinced. But
I think it's a bit of magic. If they create some
Yeah.
sort of symmetry for which they kind of partition the lower dimensional space, but but yeah,
I'm not sure.
also experimentally, it needs to be tested. I feel, because now you're testing on M and CIFR, which are pretty small, and the increment is not huge compared with. So do you think that if tomorrow you actually train on something like ImageNet, do you think you will get benefits compared with?
I think so. I feel pretty confident in these models. So honestly, sometimes when you work on projects, at the end you don't feel super confident in the final result. You kind of know all the issues. But actually, in this model, I feel pretty confident, at least for density estimation. I'm slightly less confident for variational inference because flows are, again, not as good in variational inference.
Oh, I think that so if you just use the flow,
just baseline flows, I mean.
I think that auxiliaries do miracle in some situations that are related to variational inference. But I agree with you. If you just try to use the flow to a inference problem, usually you get garbage, and Gianluigi can confirm this because he just actually did. Sometimes it doesn't recover anything. But if you use that locally, using, for example, our cascading flow approach, then you can do extremely good stuff. So it's it's more about using normalizing flow in a correct way, I would say.
I don't mean to say that flows could never work in VI. I just mean like baseline and like standard flows. They need to be modified to work well in VI.
Yeah, that's it would be actually very interesting to figure out why they converge so badly on some VI situations. It's.
I'm not totally sure. Maybe it's to do with some of the topological issues, although the same topological issues don't exist, but maybe approximate versions. I should probably maybe talk about VI a bit in my just before the time runs out, maybe, though, because I do have more slides on VI.
Okay, thanks. It would be nice, yeah.
Yeah, cool. So yeah, exactly. Just modifications. We have to modify the CIF model a bit for variational inference. Let's see how we do it. So I'm not going to go on this slide too long. So basically, we have this model of the data y and unobserved latent x. And to do VI, we introduce a model Q, and we learn its parameters using the lower bound objective here, elbow, which I've called L1. So the whole point of VI is to parameterize Q using a very expressive family of distributions. Because if your family of distributions is underexpressive, you could underestimate the variance of your posterior or have increased bias. Both are bad things. So normalizing flows are one way to build an explicit model for Q. You could just, since we have the explicit density from before, you can just plug those in directly to the elbow. But as we have just discussed, they're not really that great on their own for large-scale inference. So let's see maybe if auxiliary variables can help. So we can use CIFs to give an implicit model for Q as an integral over the auxiliary variables. And we have this QXU in closed form. So one problem is we have an implicit model for Q, so we can't plug this directly into the elbow. Instead, what we'll do is use a parameterized auxiliary distribution, which we'll call R. Let's introduce that. And then we'll be able to now write this auxiliary elbow, where instead of sampling just from QX, we sample from the joint QX and U. And then we compute this objective here on the right. All of these terms are tractable now. And if we use the implicit Q, if we were able to use it in the previous elbow, it would actually be an upper bound on this objective. So this objective adds a bit more bias, but we hope that this objective will be able to give us more expressive models, and we can improve upon the baseline explicit model, even if we have increased bias, because we'll have more expressiveness. And an important point is that, sorry.
No, I wanted to say that part of the bias is completely harmless, because part of the bias is TKL divergence between, you can see that the bias is, at least part of the bias is TKL divergence between the transformed auxiliaries and your parameterization of the auxiliaries, and that is for free. You don't care about that term. Even if that divergence was high, it wouldn't impair your fitness. So there are two sources of bias. One comes from the first Jensen inequality you use, and the second comes from KL divergence. That basically it tells you how much you are fitting the auxiliaries well. But since you are neglecting the auxiliaries anyway, so that's a kind of harmless source of bias. It's,
I guess, yeah, that's true. But then again, if you have, I guess having additional bias is bad in general. I don't know. Maybe we can discuss it a bit later.
I think that's a misconception that a lot of people do. Like a lot of people think that reweighting is good, but if you reduce the bias, you end up to important sampling, which is terrible. So it's the whole point of variational inference is that you get this bias and you get out a low variance, and it's I think it's a bit naive to think that reducing the bias improve variational inference, because again, if you want to have a good estimate,
I guess if you have reduced bias, at least in the original elbow, then you have a better fit of your variational posterior, because the KL between the two posteriors is the bias, right?
Yeah, sure. But my point that there is one term here that is the KL between the posterior of the auxiliary and the auxiliary themselves. And that term evaluate the fitness of the auxiliary model, which you don't care about. You could have a looser bound, because you could still fit the posterior completely well, 100%, zero term, and then you will have still a KL residual there. Which doesn't care about your posterior. It's just there for the auxiliary. So it's some of that bias can be completely harmless. That's my whole point.
Yeah, true. I think I'm on board with that. It's just weird to think about, but yeah, I'm cool with that. Anyway, what's nice about CIFs is that they already give you a form for this auxiliary distribution. We can just repurpose the same inference style inference thing we used before. And another thing that's nice, so if we use CIFs in variational inference, we can use a lot of the design choices from density estimation when we're not using amortization. So we can use the same single layer model, and we can use the same form of multi-layer stacking, and our inference model will have quote unquote the correct structure again. Because as we discussed, this we can invert the graphical model properly. So one obvious major difference is that this is a different setting. So you have this model now instead of data, or instead of just data, and you have a different goal. You're trying to get an approximate posterior rather than a density model. And this is kind of a sell point. I won't bother going over that. But one important difference here is that when you want to now amortize your variational posterior, which was not something you would have done in density estimation, you will now be able to do this by incorporating, let's say, a VAE style encoder at the start of your flow that maps you from data space to latent space. So you can imagine, let me just go back. I know I'm jumping around a bit. But let's say we are in this generative model here. Don't worry about the P stuff up here. So to amortize in the one direction, we put like a data node here. I should have added another figure, but anyway, we put the data node here, let's call it Y, and it goes directly into Z randomly. And Z remains random, Y is in a higher dimensional space, and that's how you amortize in that one direction. But then for the inference model R, you're not going to be able to have the same structure where you just go from here to here, then here. You know, we can't just do that kind of model because the data node will not be quote unquote deseparated properly from the rest. So the data node will have to be fed back in to the inference model at each layer. And there's a diagram in the paper. Again, I should have included a diagram, but I forgot. So hopefully that makes some sense. If there are questions on that, I'm happy to try to answer them without adding more confusion. Because I know that amortization was another thing that was interesting in the cascading flows as well. Be interesting to see how those two compare.
So what we do there, I mean, we don't do that through the encoder network, so maybe that's interest. What we do is simply we have the distribution over the latent, and we feed a linear layer to that changes the mean of the distribution of the auxiliaries.
Right.
So we have these auxiliary nodes, and then the mean of these auxiliary nodes is shifted by the data through a linear layer. That's linear because the flow can add arbitrary nonlinearity. Now it seems so okay, but because your autoencoder, is it the same thing that you're doing in some sense? Of course, we don't have multiple layers of auxiliaries, so that makes things a bit less comparable.
So the start layer is kind of essentially a linear layer, I guess, with some Gaussian noise, right? So if you have like a VAE style encoder, you have a standard Gaussian, and then you do a linear layer on top of that, basically, right, to get the mean and the variance of the Gaussian.
Mm-hmm.
Right? Does that make sense? So maybe that's a bit comparable.
I think there is some subtleties that of difference that I still have to completely wrap my mind around, because it's because my point that the role of the encoder of the variational distribution in our model is what models the posterior over the auxiliaries, which is not, it doesn't actually add anything to the inference, just lower the bound.
Right.
But it's probably
so the reason why we include this type of amortization in the auxiliaries is to invert the model, invert the graphical model that we have for this like true Q distribution over the auxiliaries, where this should actually be U1 to L.
Yeah.
But yeah, that's why we would include the data at each layer. And actually how we include the data in the auxiliary inference model is a bit more complicated. So in this direction, it's pretty simple, just at the start and then as we were discussing. But then in the backward case, we have to somehow concatenate the data onto the latent variables. So I use some like convolutional layer and then a linear to map to the same space as the latents. Or I think actually what I do is I upscale the latent variables into an image shape and then concatenate them together and then use it to infer U at each layer.
So the very, I don't know how much is relevant for your experiment, but the very nice things of our approach, of course, is that you input data node by node, and you don't input data globally. So it actually, it's much easier to encode the data because it reflects simply the data at each individual node. It doesn't reflect the whole data set. It can be quite heterogeneous and difficult to encode.
Right, yeah, I guess so. Here, I was just concerned about amortized inference. So we just take data point by data point. It's just like you can imagine it like a tabular data set, or even the image data set will be somehow turned into some kind of tabular form. But it's like you have a bunch of IID data and you're doing SGD and you amortize by sending one point in at a time. So it's not, I don't think it's as structured as the form that you're using for the amortization. It's meant to be kind of general, I guess. But I'm not sure. I don't know if I fully understand the other kind of amortization.
Well, that's specific of the fact that we apply the flow locally, right? So you can use extra structure if you apply the flow locally. I suppose that you're applying the flow globally, right?
Yes. Yeah.
So basically,
right.
we have access to the graphical structure of the model. That's why we can inject the data locally and make it flow backward so that reaches the previous node. Of course, that's not easy if you have just a global model. So that's
yes, right. It'd be nice to somehow unify these two approaches. There must be some kind of instances of almost like the same higher structure.
I do think
they're
so.
pretty similar.
Yeah, I think so. So basically what we do is that we incorporate. So what we do of sophisticated is that we incorporate the prior probabilistic model that we used for inference into the flow, basically. So that the flow kind of fill in the.
Oh yeah.
So what you do is that you incorporate the auxiliaries into your flow. So it's.
Yeah. Yeah, that makes sense. Yeah, because you in this terminology, you would be using P to construct Q. In our form, we're using Q to construct R.
Yeah.
And we're just leaving P alone.
Yeah, but the reason why usually one of the reasons why flow don't work well in inference is that P contains a lot of structure.
Yeah.
And theoretically Q should. It's a pity to throw all that structure away.
Yes.
So because ideally you would like to recycle most of that structure in order to construct Q, and that's the point of the cascading flow. That basically at every time there is a conditional distribution in the original probabilistic program, then we intersect this flow layer that changes the distribution.
Yeah.
And
that's the big difference.
I mean, you can see why you need it in real world situation, right? Imagine that you're doing variational inference on a big like deep learning model like GP3.
Yep.
That thing has been training for months, let's say. I don't know how long they trained. Now, if you try to do inference there and you don't use P for constructing Q, you will need to train it at least as much as the original model.
Yeah, right.
Well, basically, you're throwing all that information away and you're trying to retrain everything from scratch, while actually, in order to do inference, you just need to push your probabilistic model in the right direction. You don't need to change too much. Most of the structure in the posterior is structure in the prior. In most of the cases, not always, of course. Like in Bayesian neural networks, the prior is trivial, and the structure of the posterior just only come from the likelihood. In that case,
yeah, I think that's an interesting point. I guess there'd be two different applications. So when you have a lot of structure that you want to use, then certainly you'd want to use the cascading flow. When you don't really know anything, then this approach might be a bit better.
Yeah, like in Bayesian neural network, you don't gain anything from the cascading flow because it's the only thing that the cascading flow does in Bayesian neural network that it treats each bank of weights independently, which maybe is nice because you cannot tangle too much with the weights, but but yeah, so
that's interesting.
The big problem is the big problem that I think is very interesting to solve. I mean, it cannot be solved entirely, but at least to face is the likelihood contains a lot of structure. Like the likelihood, imagine a Bayesian deep neural network. The likelihood has an enormous amount of symmetries. So there's an incredible amount of structure. If that structure can be used in order to construct Q, then you get a very powerful method.
Well, actually, I worked on something that was like this once. If you use Hamiltonian methods, basically, you can encode some structure of the likelihood using the gradient, right, to build the flow. But I didn't find that it worked super well in practice. But I don't think I was doing everything optimally. It was my first PhD project. So maybe revisiting some of the Hamiltonian stuff could give you some of that structure. But it's also computationally a bit of a pain because you have to take the gradient and then the gradient again.
Oh yeah.
So, but maybe there's something there. Anyway, I should probably at least show the results of the experiments before I leave. So we see This is a toy example of mixture of Gaussians. So at the top we have CIF extensions of neural spline flows, and then at the bottom we have neural spline flows. So in the low noise regime, neural spline flows, NSF, doesn't cover all the modes. In the normal noise regime, it works well. So this noise is the starting noise of the flow. It does well, but not as well as CIF. And then in the large noise regime, it's just totally unstable. Whereas the CIF covers all modes in all cases, doesn't cover the modes perfectly here, but the elbow is higher, so it indicates better performance. And these two models are like basically as well as you could expect to do on this kind of problem. So that's pretty promising, at least. So this is a case where there's not much structure in the prior.
So are you using the augmented elbow as metric?
Yeah, so I'm using here, actually, I'm building an estimator of the marginal elbow. So these are both the marginal elbow.
Okay.
This estimator is biased positively, so it is overestimating, but I did a study on how many points you need to make sure that it's a reliable estimate, and I'm using a lot of data points to estimate this, so the bias should be quite low. Cool, and then we have these image results again. These ones are this kind of network. This was a small network. It's a bit less convincing. We had a large network that did a bit better, which I probably should have included in the slides instead. But oh well, CIF is at least doing as well as anything else in all cases. Cool. So let me conclude and then, yeah, so what have we done in this talk? We pinpointed a limitation of normalizing flows. We introduced the CIF to get over this limitation and generalize normalizing flows by adding some randomness. And CIFs have improved over normalizing flows in both density estimation and variational inference. So what are the next steps? So we can use CIFs in other applications where flows have been useful, so compression or ABC. We could also think about CIFs for discrete distributions. You might not get some of the topological benefits, but there are flows for discrete distributions, so maybe there's some work that can be done there. And maybe we can improve our choices of the model for F, P, and Q. You can even think about using CIFs as the inference model and other CIFs. You can maybe gain some sort of new compositionality in that regard, but I haven't really looked into that deeply. And I want to thank my co-authors as well. So Rob was actually the first author on the density estimation paper. He's actually more of the topology guy than me. And then these are our supervisors. So he's supervised by George. We're both supervised by Arno, and I'm supervised by Dino, who worked on VI stuff. Cool, thanks. Sorry for running over and actually arriving early, but
no, it's my fault. I've interrupted you all the time. It's just that
that's okay.
I had some thoughts, and now that I think about, so thank you very much. It was really fascinating. Now that I think about, I think that there is a very strong connection with your CF. What was CIF or? And we are using this backward linear Gaussian model. I don't know if you remember. The cascading flow paper.
Yeah, it sounds kind of familiar.
Which it doesn't work very well, to be honest. And you're using kind of this backward auxiliary network. So actually, I feel that it could be actually quite straightforward to unify it. Basically, instead of having the backward linear Gaussian model, to have your form of backward auxiliary network through these encoders.
So for R, basically, right? The auxiliary distribution.
Yeah. So the idea. I don't know if you are familiar, but if you act locally, what you need to do is to have a way of modeling collider dependencies. So when you have two arrows pointing at the same variable.
Yeah.
And for that, you have to send stuff backward. So you have to send information backward in order to couple it. So right now we're using a linear Gaussian model, and it doesn't work very well. But I do think now that we can use basically the same approach you're using for propagating backward the auxiliary variables. It's something we can use for dealing with colliders.
Oh, interesting. Yeah. Well, I guess that would make sense in the regard that you would want to have maybe a more expressive auxiliary model that matches the structure of the variational model. Right?
Yeah, I mean, my principle for using a simple auxiliary model was that the flow can reintroduce any sort of expressiveness. But I have to say, in practice, it doesn't seem to be the case. In practice, it seems that we cannot model more than linear colliders. So I think
maybe it is actually a problem of the bias, the additional bias. I don't know. I think I'm not totally. I would say I'm not 100% convinced that that additional bias doesn't hurt you, because I think that objective is encouraging your Q model to get close to your R model, right? Or your R model to get close to your Q model.
I agree.
So if they're,
it could hurt you. The fact that
I don't have a good argument. I don't have a good argument, to be fair, but it's just intuition that I have. I think it could still hurt.
I do agree that it could hurt, but the way it could hurt, it can reduce expressiveness to the. So if you have a bad model for R, then your auxiliaries could lose expressiveness because they're trying to be simple. In that case, yes, it could hurt. Although my intuition is that it is not a big deal. My intuition is that if you have enough auxiliaries, there is enough nonlinearity there for actually driving the proper convergence of the rest of the network. But I do agree with you. You could find situations in which the auxiliaries are too simple because they're trying to match a simple target distribution on the other hand.
Yeah, right. I think another thing too is if you have a lot of auxiliaries, if you maybe don't have structure in the inference of these auxiliaries, then you might have a variance blow up. Because imagine, so
I mean,
our
you
problem,
need to scale them, right? I do scale the weights, in which case then, but you could, I can imagine that, yeah.
So in the CIF model, just for some additional perspective, we were initially concerned that we would have variance exploding exponentially because our model is a nested Monte Carlo model, basically, right? Nested on the auxiliary variables. And you have, let's say you have 10 layers of this nesting. This should have an exponential blow up in the variance, right? But I think the fact that we can invert this model properly using the bijective structure allows us to control the variance of our objective, because the inference model will be pretty good. Maybe what you're seeing is a bit too much variance because you're using a simple auxiliary model.
Yeah, it could be. Yeah.
I don't know, just conjecturing a bit.
Anyway, fascinating work. Thank you very much.
Yeah, thanks for having me.
Probably I will send you a mail soon, because I would like maybe to keep a bit of mail conversation to discuss some ideas, because I think we have a lot of, most of the stuff you guys have been using is stuff that I've been thinking about. To be honest, not at that level of depth. For example, I never actually talked about layer. Well, we did talk about layer-wise auxiliaries for actually neuroscience reason. And that's why a bit of pity that Nas left, because we had this work for a biologically realistic backpropagation, which relies crucially on the invertibility of the of networks. And there we actually do use layer-wise auxiliaries. And actually, you can show that this gives you a model of backpropagation that could be actually implemented in the human brain, because it doesn't require a lot of unnaturalness that you actually get. And actually, that is very nice. You should actually definitely talk to Nas, because it's, at least I would recommend to do that, because there actually is a lot of insights on this. But what we actually do there is that instead of having full invertibility, we have kind of a we have an infinitesimal version of invertibility at each layer. So it's a kind of infinitesimal perturbation at each layer, which
so it's some kind of sounds like a gradient flow almost.
Just read our paper. Actually, it's
Which one?
It's called the gate prop.
Maybe you can here, I'll look it up. Gate prop.
We actually got a spotlight at NeurIPS.
Oh, interesting. Let me see if I can find it. Gate prop.
So the goal there is to be biologically realistic, so it's not necessarily to improve performance, but I think there are some insights in that paper that you could find interesting.
Okay, cool. I'll check it out, thanks. I can't find it. Let me see. Maybe I'd find it on your Scholar page.
Yeah, strangely it's already not already in the new RIP proceeding, but I guess it takes some time.
I should look there as well.
Yeah, but it's strange that it's not indexed, but I guess it takes some time.
Yeah. So this is recent, you said, right? Oh, gate prop. Oh, okay. Now I got it.
Yeah.
Cool.
Yeah, it's quite recent. We submitted to last new RIP, so.
Oh, I spelled gate. I had the different kind of gate. G-A-T-E.
Oh yeah, I understand what you mean. Yeah.
You have gait like walking.
Yeah, it's like walking.
Cool. Okay, I'll check this out. Thank you. I
mean, I don't know how much is relevant for you, but I could imagine that you could find it insightful. I thought the goal was neuroscience.
Yeah, I don't know much about neuroscience, but I'll give it a shot.
Yeah, I mean, there is not much neuroscience in the paper at all. The only reason the goal is neuroscience because the main goal of that paper is to get a learning rule that can be implemented biologically.
Right.
But the paper in itself doesn't have much neuroscience.
Cool. Well, I'll check it out anyway.
Okay. Anyway, thank you very much. And
yeah, thanks for having me. Hopefully, it was a great discussion.
See you soon. Bye.
Thanks. I'll be in touch. Bye.
Bye.